the EEE 334 midterm review. Just going to do a few problems out of the book. I encourage you to do the problems first and then watch us complete them. This particular one is problem 2.50. It says, for the circuit in figure 2.50, use superposition to find V out in terms of input voltages V1 and V2. Assume it's an ideal op amp. So V1 and V2, you can see that the only difference is the sign on the second sine wave, and one's at the inverting input of the op amp, and one's at the non-inverting. Obviously, the inverting input of the op amp is the one with the minus sign. So if you don't remember superposition, basically what we do is we take one of the voltage sources and short it so that it's to ground and solve the output for that one. And then we do the same thing for the other voltage source. So we'll start by shorting out V2. So this will go to ground. And now we want to solve for V1. So this is pretty much the inverting op amp, which we already know the equation for is V out equals the feedback resistor over the source resistor times the input. So we could put in the feedback and the source resistors. Cancels out. So V out is going to equal 10 V1. Or I'm sorry, negative 10 V1 because it's an inverting op amp. You can check that real quick. I encourage you to check and always make sure, and it's good practice for your nodal analysis on op amps. So we know that this current and this current have to be equal through the op amp because there's no current going into the inputs of the op amps. Since this is shorted, there's no voltage over here, so this is 0. So this is 0 as well. That means V1 minus 0 over R is equal to 0 minus V out over 10R. And you can simplify that out to get V out equals negative 10 V1. So it does work out. So now we can just plug in our V1. So V out 1 equals negative 100 sine 2 pi. Okay, and now we can move on to the second one. So we're going to short this guy here. And now this is like a non-inverting op amp. We know the equation for that is V out equals RF over R1. Oops, sorry. Plus 1. So the only problem here is that we need to solve for VI, because in this case, VI would actually be right here. So we need to do a quick voltage divider on this to find that input. So VI equals 10R over 10R plus R times V2. We're doing 10R over 10R plus R because the voltage drop across this resistor is going to be the same as the voltage at this node. So VI is going to end up equaling 10 over 11 V V2. So now you can plug all of that back into this equation. V out 2 equals 10R over R plus 1, 10 over 11 V2. These R's cancel out. And then this will be 11, so this 11 will end up canceling with that 11. And you get V out 2 equals 10 V2. And you can do the same thing and go back and check your work. So you have 0 minus 10. So this is now 10 over 11 V2, which is going to be the same at that node right there by our laws of op amps. So 0 minus 10 over 11 V2 over R is going to be equal to the same current, 10 over 11 V2 minus V out over 10R. And you do some algebra and it ends up being, it ends up working out. So V out 2 equals 10 V2. So now you can plug that back in to our V2 equation, so we can solve for V out 2 equals 10 times that, so 100 sine 2 pi times 60 plus. Okay, so now that we have our voltage out 2 and our voltage out 1, to find the V out, we just add those two together. That's how superposition works. So you can see that these are the same, but one's negative, so it's going to cancel out. And then these two are the same sign, so V out is going to equal this plus this, which is 2 sine 2 pi times 1000 t. And if you wanted to do it not superposition, you could go back and check your work and make sure that it's the same. And so you know that we already solved for this as 10 over 11. So this is, just to check your work, so V1 minus 10 over 11 V2 over R equals 10 over 11 V2 minus V out over 10R. So multiply this over here and you get 10 V1 minus 100 over 11 V2 equals 10 over 11 V2 minus V out, which will give you V out equals 10 V2 minus 10 V1. So that's exactly what we got before. Minus 10 V1 and 10 V2, and then just add them together to get V out. So that's it.
Hi guys, this is review for midterm of 334. In this question, we're going to work with diodes. The question tells us that if V1 is equal to 1 volt, how much current flows through the resistor R1 using the full exponential equation for the diode. The diode will carry 4.5 milliamps at 8 volts. At 0.8 volts forward bias, and the thermal voltage is 25 millivolts. It gives us a hint, tells us to calculate the reverse leakage first, but then we iterate. So to calculate the reverse leakage, we're gonna use this equation. We're given the ID for this, this particular diode. We're also given the current and the VD. So we rework this equation so we can isolate the IS. That's just simply moving this term over. But before moving this term over, we want to also make a note that because it's strong forward bias, we can get rid of this term, goes to 0. So we're left over with IS equals ID over either the VD over VT, thermal voltage. So now we plug in our numbers. Our ID is 4.5 milliamps over e to the 0.8 volts over 0.025 volts. After calculating that, we get 5.7 times 10 to the negative 17 amps. So now we got IS, and we can put this term back in here so we can solve for the ID in this particular case. So we'll take, in our circuit, we're going to do a KCL. So we'll start with the 2 volts, or ID equals 2 volts minus 1 volt minus the VD. And it's all over the resistor R1, which is 1K ohms. Working this out, we get that ID is equal to 1 volt minus VD over 1K ohm. So now we got this ID, we get that ID, we can set them equal to each other so we can try to work out the VD. So 1 minus VD over 1K ohms is equal to 5.7 times 10 to the negative 17 times e to the VD over 0.25 volts. So we divide over, because we want to isolate the VD. Divide over, and then 1 minus VD on this side over 1K 5.7 times 10 to the negative 17, and that's equal to E VD over 0.025. We do the ln, take the ln both sides. So we're left over with ln of 1 minus VD over 1K, which at this point, 1K knocks these 3 of these guys out, so we're left with 5.7 times 10 to the negative 14 equal to VD over 0.025. We're going to multiply both sides. 0.025 VD is equal to ln of 1 minus VD over 5.7 times 10 to the negative 14, all times 0.025 volts. At this point, we can start our guessing, our iterations, and we can begin with our given 0.8. So at 0.8, we got that our VD is equal to 0.025 volts, ln of 1 minus 0.8 over 5.7 times 10 to the negative 14. And after doing the calculations, you can enter this on the calculator, it'll be a lot easier. We get the answer to be 0.076
Should write a little bigger.
0309. So then we take this value and plug it in place of 0.08 for our next guess. So it'll be BD equals, and I'm gonna shorten it down at 7.6. That's our next guess. So it would be BD equals 0.025 volts, ln of 0.1 minus 0.076 all over 5.7 times 10 to the negative 14. After working this out, we get that our BD at this point is 0.072 6. Then we'll go one more time just to make sure that we're pretty much there. So our next guess becomes BD equals 0.025 times ln of 1 minus our value here, 0.07266, and it's all over 5.7 times 10 to the negative 14. This value gives us 0.0729. Which at this point, we're pretty much done. I can encourage you guys to give it another couple more tries, a couple more iterations, and you'll see that this is going to be our value for a VDD that we get, rounded up. So that's our value for a VDD. So now we can go back to find our ID by using our main equation over here. I'm going to try to fit it in this corner here. So now we got the ID is equal to our IS, which is 5.7. That's 10 to the negative 17 amps. And then times our E with our VDD that we found, which is 0.0729 over our thermal voltage, 0.025. And we get an answer of our ID through the resistor to be approximately 27 milliamps. And that's the current that will be going through our resistor 1. And our VDD that we found was solved by iteration. And that's it.
All right, guys, we're going to do one more problem. This is a MOSFET problem. It's number 5.44 in your book, so go ahead and give it a try, and then you can follow me along and see if you do it the same way as I do. So it says design the circuit of figure 5.44 to establish a drain voltage of 0.3 volts. So we know this drain equals 0.3 volts. Then because the current is 0.1 milliamp through the circuit. The threshold voltage, Kn prime, L, W are all given, and it wants us to find RS and RD. So these two resistors right here. First things first is going to be pretty easy to find RD because we know the voltage on one side of the resistor, we know it on the other, and we know the current through it. So obviously, we can just use Ohm's law and find that resistance to be 7 kiloohms. Now the RS is going to be a little bit trickier because we don't know what VS is, and so we're going to need to use the current equation in order to find out what VS is. So first things first, we need to figure out if this is in saturation or in the triode region. And we know that for saturation for NMOS, VDS has to be greater than or equal to the overdrive voltage. So in other words, VDS has to be greater than or equal to VGS minus VT. We can cancel out these sources if we want to, just to make it a little simpler. And then we can plug these numbers in. So our drain voltage is 0.3, greater than or equal to our gate is 0, and our threshold voltage is 0.5. So 0.3 volts is greater than negative 0.5 volts. So it is in saturation. So now we know our saturation equation for NMOS is 1/2 Kn prime W over L VGS minus VT, or the overdrive voltage squared. So now we can go ahead and start plugging these numbers in. 0.1 milliamp equals 1/2 400 microamps per voltage squared. And then the width and length, those units actually cancel out, so it's just 5 over 0.4. And then VG is 0. So 0 minus VS is what we're trying to find, and then VT is 0.5 squared. So now you can see we're going to have a quadratic because of that square. So I'll just go ahead and write 0.04 equals VS squared. This is when you square this out, plus VS plus 0.25, subtract that over. All right, now we can use our quadratic formula. And we're going to get two values. We'll get negative 0.3 or negative 0.7 for VS. Obviously, only one of these numbers is going to work out for us, because for an NMOS to be on, the gate must be greater than the source by a threshold. So the gate is 0. We don't know what the source is, but we know the threshold is 0.5. So that means that the source voltage needs to be less than negative 0.5 volts, and negative 0.7 is less than negative 0.5. So that is our VS. Now we can use our Ohm's law to solve for RS. And you'll get RS equals 3